Okay, hi everyone. Yeah, I'll just be sharing my video. Okay, so today I will be touching on a quite interesting topic called geometric deep learning. And I think this is something that is quite exciting because I really think that the focus right now is on like how to make models more generalizable, able to apply on more context, more like using very few training examples, you can learn more. Okay, and actually geometric deep learning helps a lot in getting all this out. So let us see what is geometric deep learning. Okay, there will be quite a bit of math at the beginning and also later in the middle, but I tried to reduce the amount of math. Yeah, for the full package, you can feel free to read the book. It's called Geometric Deep Learning. And over there, they talk about a lot more things, like how to do geometric deep learning on geodesics and gauges, which involve quite a lot of integration, which I won't be covering today. Okay, so without further ado, let me give you the background of why I'm intending to share this. It's because actually a lot of the deep learning revolution that you see in the past like 5-6 years actually has a lot to do with the neural network design. So starting from like convolutional neural networks, actually before that it was like perceptrons, multi-layer perceptrons, convolutional neural networks, then recurrent neural networks, transformer models. Yeah, and all this are actually quite important because these different networks are meant for different kinds of problems and they work well for the different domains. So it can be seen that actually the neural network is actually sort of fine-tuned for a certain kind of data, like for image data, like convolutional neural networks, for sequence data, recurrent networks, or like transformers. So there's a lot of innate invariances and symmetries that are present in this network that actually help to let the network learn faster and learn better. And if we can distill out all the symmetries and invariances, we can actually create new network structures that can be used for new domains, or rather improve on existing domains as in input domains by exploiting certain invariances that are suited for that domain. So yeah, you all heard about the no free lunch theorem, right? So yeah, in the no free lunch theorem, basically it's saying that no network architecture is the best for everything. Okay, but actually, for a particular domain, there can be a best network, and the best network will probably be tailored by the network structure. Yeah. Okay, so the motivation for them is basically to use this idea from the Erlangen program. So in the past, back when like geometry first started, like there was basically this guy called Erlangen who created a way to unify like different shapes in geometry using some characteristics, like for example, angle, distance, area, and so on. Yeah. So basically all this here, it's basically like some ways to classify these different like shapes, geometrical structures, and then it sort of finds a way to like unify all of them. So similarly in deep learning, we can actually try to find these invariances and these symmetries, okay, to basically characterize the structures and sort of use them in new structures as well. So yeah, let's begin. Yeah, just feel free to ask me any questions if you want in the middle as well. There's actually more than enough time. I have about 50 slides. Okay, so about 2 minutes a slide. We won't overshoot. Yeah. Okay, so let's give you the broad framework of geometric deep learning. So there are a few G's in geometric deep learning, namely the grid structure. A group structure is like a closed group where it's commutative under addition, multiplication, and so on. So like for example, abelian groups. Yeah. So there's also graphs like molecules, like also like protein folding, they also use graphs. Social network uses graphs, where basically you have nodes and edges connected to each other. And lastly, we have geodesics and gauges, which are more suited for like those deformed structures like human bodies. Gauges are like local fields on a particular point. So this part I won't cover today because this part is more complicated. Okay, so what are they used for? Like grids, basically they are used for stuff like images, because image data is like pixels, like 2D pixels that are very suited to use on grids. certain sequences can also be 2D and they can be used in a grid-like structure as well. Or you can use a 1D grid, like a 1D CNN. Yeah. So there's also like for groups is mainly like homogeneous spaces, which is a math term that talks about like certain groups that satisfy some criteria. Okay, we won't actually be talking much about groups as well. Graphs are more like for a lot of data, actually, they can be suited for graphs because as long as there's connection between different elements of the data, you have nodes and you have edges, then those are graphs already. And then lastly, for geodesics and gauges, you can have like manifolds, meshes that are implemented on top of that. Yeah, I just pause here for a while. Do you all have any questions so far on the broad framework of geometric deep learning before we go into the details?
Yeah, I don't quite get what the taxonomy is or what the categorization is.
Oh, okay. So these are basically the structures that data could have. So like a data could be in a grid-like structure, or it could be in a graph-like structure, or it could like potentially be in some form of geodesic. So these are like the broad categories of the types of data that we can encounter in the wild.
Okay.
Yeah, so what it's saying is that for different kinds of data, you can use different kinds of structures to better handle it.
So for example, where is tabular data here?
Tabular data would probably be in the form of like a grid or it could be graphs. Okay, maybe graphs. Graphs is a better data structure for that.
Okay, and like where would time series data be?
It's either graphs or grids. Yeah. So actually it is quite, how would I say? Actually, grids can be represented as form of graphs also. So
yeah, exactly.
yeah.
Okay,
So I would say that the focus, I mean, I read through the whole book. I think the focus would mainly be in the grids and the graph section, which basically saying that your data can have different kinds of data features, and these features can be interlinked. So yeah, if you know how it's interlinked, you don't have to learn the weights or the linkage between the nodes over here. Like over here, if you know how your data is structured, you can already fill up all these edges yourself. If not, you have to learn them from your data. So I would say that tabular data is a very unique case where most of the nodes are all not links. They can be independent features, but maybe some of them can be linked like that. Like for example, if you have indicator of maybe obesity as like diabetes, they could be linked. Then there could be one arrow here. Yeah. In fact, actually in tabular data, this arrow may not be like a fixed arrow. It might be in a certain probability because not everyone has that connection. So yeah, it's a more like soft graph structure. It's not a fixed structure. Yeah. Yeah, Prof, did that answer the question?
Yeah, I mean, there's a lot of overlap between these categories, but okay, you're saying that it's going to be useful to have this view, this categorization, if you will.
Correct. So actually from one domain, what works, if you can actually express a certain domain in the structure of another domain, you can use the similar structure of the network to express your ideas. Like CNNs were quite successful for images. So if people have managed to like successfully express images in terms of, express some other domain in terms of an image, you can use a CNN architecture to do it. For example, Google did something on audio. They put the audio in a 2D image, and yeah, they can use CNN architecture on it as well. So if you can like evolve your data structure to be one of this, you can use similar techniques for these structures. Okay. Anyone else has any questions for this? Okay, I'll be moving on. So these are the kinds of invariances that we expect to find in certain architectures. So like, for example, like perceptrons, they put their functional regularity. It just means that like each neuron here like, encodes a certain function. And then you can actually swap the two neurons in your perceptron. You can like swap these two and then it will not affect the output. If you swap the input and the output weights along with your nodes, you won't affect the output because each node is like invariant in its operation. So the operation here won't change, even if you swap the position. Yeah, so I presume that's what they meant by function regularity. This is not in the book at all. So this is my own interpretation of it. Okay, so for CNNs, it's quite well known that this is translational invariance or equivariance. We'll cover more in detail. So this is actually Rohan's pet topic. So Rohan also implemented more like filters on rotation and scale equivariance. So all these are also will be touched upon. This is actually under group CNNs, where they apply a group symmetry operation to the filter. LSTMs, long short-term memory, is a form of recurrent neural networks. So this, they actually have this property called time warping. I feel this is a little forcing it, but we'll go through what is time warping later. It means that like it can handle data that has like dilated time, which means that if your input sequence is of a form that actually is of a different like sampling frequency, you can still handle it. Okay, so LSTMs. Then we move on to deep sets or transformers. Maybe you just touch on transformers because it's the more popular architecture in like sequence data, or like mainly used in NLPs, natural language processing. So this exhibit permutation invariance, because actually you can express like transformers as a form of graphs. We will see that later. So similarly for graph neural networks, is permutation invariant because you can swap the order of your nodes, or rather you can swap the, if you represent your nodes in terms of like row order, you can swap the row order of your nodes. Like for example, node 1 and node 2, you can swap the row order in the matrix representation, and it would still be like, let's say this is node 1 representation, and this is node 2 in the matrix representation. You can swap the order, and it will still give you the same output. Okay, so this is what they mean by like permutation invariance in GNNs. And lastly, for like isometry gauge choice, this intrinsic CNN is using some form of like geodesic properties in order to like simulate a deformed surface area. So these are actually some of the more popular architectures, and like how these symmetries can actually be derived from it. I feel like not everything in these architectures are explained by symmetries, but definitely knowing the symmetry and some invariances can actually help to generalize from more limited data. Yeah, so I mean, the case in point is like for CNNs, if let's say we have the CNN architecture where you have filters, and each filter will basically, that's my drawing. You have certain filters, and each filter is basically applying the same grid to like different points in the diagram. So you can actually learn a shared weights. Like if you want to find out a filter for a plus sign, your filter could be like ones for this particular grid squares, and then you can find out which parts of the images have a plus. Yeah, so this is basically saying that if you have an image with a plus on like the top right corner, if you learn this filter, you essentially can generalize to an image with a plus at the top left corner. Yeah, so because you already know your image is like it should be translation invariance. Like if I shift my image from one point to another, I shouldn't change my classification if it's a classification problem. Yeah, so this is something that perceptrons don't do, or multi-layer perceptrons don't do. And that's also why CNNs can learn actually faster than MLPs in terms of like doing an image classification. You can try using like Cypher 10. If you use a MLP on it versus using a CNN on it, the CNN would learn faster and with better accuracy. It's because of this innate invariances in the filters applied to the different patches of the image that an MLP will need to learn from scratch all the different patches, like how to classify a plus on the top left. It needs to learn this part. It also needs to learn the middle part. It also needs to learn the right part, because what you learn from one structure cannot generalize across to the other sites because it does not have the invariance built in an MLP. Okay, so this is just a rough idea of how learning the invariances or symmetries can actually help you to generalize better. Okay, any questions so far?
I don't know if you're going to touch on this, but I don't quite understand the permutation invariance.
Oh, yes. Permutation invariance just means the ordering of your nodes in your matrix. Doesn't matter.
But what matrix you're talking about?
Yeah, I will cover that in one slide later.
Yeah, because I thought in this thing the graph is your data. It's like it's like, is that true? Is the graph my data?
Yes, the connections between your graph. Basically, there's two parts in the graph neural network. One is the data from the vertex, and one is from the edges. The edges has a connection, and the vertex is like certain information that you feed in at the start to this node. Yeah, so when you do like permutation, you actually reorder your H matrix, and in your H matrix, there's also like there's this matrix called the adjacency matrix, which covers like which nodes are connected to which other ones. If you do a permutation operation to it, the overall graph structure shouldn't change.
Yeah, I know, but I thought the invariance or inductive bias is with respect to not the data set, but a specific data sample. For example, I have a picture and I have a plus sign on, in the top left or bottom right. That's the invariance that you're talking about. But permutation, when you're talking about, it sounds like you're changing the data. You're saying if I reorder the data,
Yeah. I get your point there, but actually you are not exactly changing the data per se, because okay, let's just give an example for this permutation invariance. Let's say you have, like, for example, you have a graph structure like that. So like node 1 is linked to node 2 on the left and node 3 on the right. If it's permutation invariance, if I change my order of my nodes, so node 1 is linked to node 3 on the left and node 2 on the right. So because it's permutation invariant, these two structures, they call it isomorphic. Basically, you can transform from one to another, and basically that's why it's called permutation invariant. You can change the permutation of your ordering of your nodes while preserving the connection structure, and it will still be interpreted in the same way.
yeah, it's fine. I mean, you're going to talk about this, right? So will you focus on GNNs or will you say stuff about GNNs?
Yeah, the focus will be half-half, like CNNs, GNNs.
All right, thanks. Yeah.
Okay. All right, so I'll just continue. For the rest, feel free to clarify anytime, because I think I'm going to start on the math part, and the math part is quite foundational for the rest of the session. Yeah. It took me quite a long while to understand the math also, so I'm digesting it for you. Okay, so why? First, I want to start with the importance of this topic. So it's just to convince you that geometric deep learning is actually important for like generalization and a lot of other things. It's because, okay, imagine this. If you knew all the symmetries that are present in your data set, for example, if let's say you have MNIST data set, right? So you know that, like, let's say your MNIST data set will have like a 6 here, and maybe your MNIST data set will also have like a smaller scale 6. You also know your MNIST data set can also have like rotated 6. Okay, maybe rotated is a bad example. Maybe translated 6. Okay, rotated is bad because if you rotate the 6, it becomes a 9. You see, so yeah, MNIST, you shouldn't have rotational symmetry because of that. Yeah, so if you, let's say, do a translation, so this is a translation, and like this is a scale. So if you already know all these are in your data set, what can you do? You can actually build in this into your structure of your network, or like do the data augmentation to learn. But of course, doing in the structure is better. I'll explain why later. And if you can already model all this, and this is your certain class, like maybe class 6 compared to like a class 4. If you can do all this, then essentially you just need to know one sample point here. And then from this one sample point, you can actually like because all of them are like equivariant or invariant. Okay, it depends on the context. But if let's say all of them are similar, you just need to learn one. You can map to all the other possibilities, and they all be classified the same way. So if you are given this input, or this input, as long as you already know, like, let's say you already know that this 6 classifies to 6, then if I give you like this one, because of your invariance present in your structure, you can also use this to classify this as a 6. And same thing for here, you can use this to classify as a 6 as well. So because of the symmetries that you have learned, you can learn the data with just new data with just one sample. So I mean, this can be used in stuff like one-shot or single-shot learning. Of course, if you can like come up with all the different possible classes, you can do zero-shot learning. Yeah, so this is why symmetries can be so powerful. Okay.
No, but you haven't addressed how, if we know all the symmetries in the class, you can learn one sample, right? Based on what you're drawing, it's okay. I can buy the idea that you require maybe less data, but How does one data come in?
If you already know all the symmetries present in that particular class, all the perturbations are based on a symmetry or based on multiple groups of symmetry, then knowing one is equivalent to knowing all the other types of symmetries, right? Because you can just apply the symmetry operator on them. And so you can like extrapolate from one data, you can extrapolate to many data. Or rather, all of the different 6 that you encounter here will all be treated the same way by your model, assuming that your model is that particular symmetry invariant.
No, that's assuming we already know the model in hand, right? That's why you say, okay, well, now we have this class, we are able to classify it. But how do you even arrive, like what you draw on the screen, the Venn diagram looking thing?
Oh, that's just an example. Okay, I mean, this Venn diagram looking thing is basically saying that given like one data set, I can and maybe another data point here. So maybe this is like a translated data point, and maybe this is the not original data point. It's saying that all this will be classified in the same. I mean, if you want to treat it, this will be classified in the same latent space or manifold, and you can do so automatically without looking at this class here, because when the model takes in a translated version of the input, it will automatically classify in the same manifold due to the structure of the data, structure of the network.
What symmetry again? You're just talking about the manifold itself, is it?
Yes, correct. So the manifold will be clustered together by the symmetries that are modeled in the network, like for example, translational symmetry. If your network structure has translational symmetry like GNNs, an image that is translated will be in the same part of that manifold as your non-translated image, automatically without you learning anything. You get what I mean, Dylan?
No, then it doesn't make sense that if you knew all the symmetry is a derived product, right? It depends on whatever input you feed the model.
Yes, correct. That's why I say if you know all the symmetries, you see. So if you already knew what is present in the real world, of course, this is a very ideal assumption. And in real life, usually you don't know all the symmetries, or rather you cannot extend to everything based on just one class. But if you could, then one sample per class would be sufficient to learn already. I'm just highlighting why this can be, this can help you to learn more with less.
Okay.
Yeah, I mean, you can just treat this as the ideal version of like how you can learn stuff. But of course, in real life, you may not be able to classify all symmetries because real life, maybe you have noisy data. Your noisy data cannot really be represented by a certain symmetry because it's like some deformation of your data.
The symmetry is just a manifold structure, right?
No, symmetry is different. Symmetry is like what we saw in the previous slide, you see? Like all the like translation symmetry, permutation symmetry, and so on. Yeah.
No, but symmetry isn't invariance.
Okay, so a symmetry is related to invariance because if let's say a transformation is symmetric, the transformation will be invariant in a certain property. It's like what Shabir shared the last time about Noether's theorem. Like there's some invariance in a certain metric, like for example, energy. So let's say if we talk about like for example, translational invariance. So translational invariance, maybe have a letter T here and a letter T here. So over here, it is symmetric in some way. So maybe it's symmetric by reflection, or it could be symmetric in terms of like this particular image is the same from here to here. Okay, I'm not too sure what symmetry this should be called. Translational symmetry? And I'm not sure what's the name for this kind of symmetry, but basically if you have some invariant property, you usually derive it because of some symmetry in the input. Yeah, so it's quite related, symmetry and invariance. Okay. Yeah, Dylan, you have anything else?
It just I think it's weird to say that a symmetry is related to the class. It's more imbued to the specific learning algorithm that you select, right? That means other than that, you have no choice. And once you deploy or once you select the model, you have no choice on what symmetry you can get. It's still all depend on the model. Then it shouldn't be related to class anymore.
Right. But if you model that symmetry in, you can learn with just like a few data points or just with one data point, you can exploit all the symmetries in your model itself to map out like all possible inputs for that class. So it's related.
maybe it's because I see the screen, it say we can learn the class with one sample, that's why I'm getting very edgy. Because okay, even if you have a very good model, which is, let's say we are trying to predict a linear regression, right, a straight line, you have one node, so it's essentially the wx plus b.
Yes.
What are you learning for the class here with just one sample then? You're just learning the weight, is it?
Yeah, I mean, in this case, the wx plus b, you're just learning the function, right? So if let's say all your inputs satisfy that function, of all that class, all the inputs satisfy that function, like in terms of
right, but that's the structure then. Then why do we talk about if we knew all the symmetry in each class?
so actually, if you is okay, let's say we talk about SVMs. Okay, you have two input features space, right? X1 and X2. And then let's say you have like a dogs versus cats classifier. Suppose you have a function that has, in terms of like its hyperplane, you separate like the x's from the o's by a certain line. So like, for example, SVM, you separate from this line. So assuming that this line it sort of represents like all possible classes in one side and another, basically it's linearly separable. Or maybe if you apply some kernel, then it becomes linearly separable. So if you, let's say, talk about SVMs, this will be something like functional regularity that was touched on in the previous slide. So with just like one sample here, like because I already know how this hyperplane separates with this separating line. With just one sample here, I can then already classify this as maybe dot, because I know that this model obeys this symmetry whereby to the left of this line is one class, to the right another class. So yeah, with just one sample, you can actually classify already, because if you already know how it divides in the manifold. So yeah, similarly, you can treat this as like how it divides in the manifold like that. If all your different like perturbations of the input fall within like one part of the space and the other perturbation fall in another part of the space, you just need one sample to determine like what is the supposed class for it. Does that make sense?
I think it makes it a little bit more confusing, because for the SVM, you're just saying that I have the classifier and I can know what it, like you haven't discussed anything about symmetries in your SVM example, right?
Yeah, that will be the next few slides.
Yeah, no, I mean, so can like to follow up on Dylan's question, can you explain how, if you knew all the symmetries, how you would learn the class with just one sample?
It just means that if you have one sample,
Yeah,
you can then form this like region whereby all the samples should be in.
okay, so you're saying you can know the decision boundary?
Yes, correct. With
So
just
you're
one
saying that
sample, you
knowing,
can form,
so you're saying knowing the symmetries is equivalent to knowing
you know the class boundaries. You can like sort of extrapolate the space of all possible input samples for that particular class.
So let's say you take images, you know that all images, like in all vision problems, you have translation symmetry.
Correct.
So how is knowing translation symmetry allow you to classify?
Yeah, so for example, if your training set contains, if your training set contains this number like this, contains a 6 on the top left, then in your decision space here, you can see that maybe this is the 6 on the top left. But because it has translational symmetry, the 6 at the bottom right will still be in this particular circle here. Or I mean, it could be any shape. But basically in this region whereby it's still the class 6. So knowing this one particular sample, you actually are able to like generalize and then know that this is the classifier space for number 6.
But you don't know how to separate 6s from 7s, because 7 also has translation symmetry.
Right.
So I guess that's what everyone is confused with, right?
Yeah. So
like what this says, that instead of a lot of data, I can have very little data or just one sample. But
so you already learned this is a 4, and then it obeys translational symmetry, then another 4 over here. So in your training set, you just need like maybe this particular point here.
Oh, but in your
example,
but in your example, you've already separated 4 and 6. You're already assuming you know how to separate 4 and 6, even though both have translation symmetry.
Correct.
How do you
So,
separate 4 and 6?
so you must have a single class example. Then you train on that example. Then your network can actually learn the class boundaries.
But then there's nothing to learn.
Why? Because you have a single sample of 4 and a single sample of 6. You already know the true labels for these two, and you can learn from them. So, for example, your training data can be like a particular 6 and a particular 4 like that.
But how are you learning to separate 4 and
Then
6?
maybe you just apply softmax. Basically, you just apply this thing called cross entropy. And basically, you do the normal classification loss with just 2 samples alone. And because of the way the CNN is structured, you can then perturb your input with like certain translations, and it will still be it'll still be interpreted the same way.
Yeah, but here the translations don't have any. I mean, they're extraneous. They're secondary. You still need to be able to separate 4 from 6, and you're going to use cross entropy loss to do that.
Correct. So you need to learn with one sample.
Yeah. So you're not learning anything. This is the usual learning, isn't it, Changmin?
It is the usual learning. I'm just saying that if we have the particular symmetry or invariance embedded in the network, you don't have to learn. So let's say if we don't have the translational invariance or equivariance embedded in. So let's say we were to use an SVM, if we were to use a MLP, what will happen is if for CNN, maybe you just need like one example per class. For an MLP, I also need to train it with like a 6 here, with a 6 here. I need to train it with all the possible perturbations of this 6. And also for 4, I need to train with like different examples of 4 at different areas of the input in order for the MLP to learn. So with that, I'm saying is that like for example, CNNs, you probably just need one example.
It's
and
okay.
you can learn all possible configurations.
No, Changmin, I think we're confused because I thought, and I think Dylan thought, you were trying to say something different here. But if like what you're saying is this is, I think the intuition we all have about CNNs right now.
Yes, correct. So there's nothing different from that intuition.
Yeah, so I don't think you're trying to say anything about that I can reduce the number of samples I need to learn.
You can reduce the number of samples per class that you need to learn.
But it's what we already have.
It's what we already have with CNNs. Yes, yeah. It's nothing new here. It's just the.
Dylan, does that make sense? I think we're trying to put too much on this slide. Say that it's trying to say something different. Dylan, are you in?
I'm a bit lost, but here's how I understand from the discussion here. In order to establish, so my initial confusion is in order to establish the symmetry, you need those data samples to learn the boundaries, right? And right now, instead, what I'm seeing from the text is you can, if you already know that prior, you can learn the class by using one sample. But that doesn't make sense from what I was saying earlier, right? Because in order to learn the symmetry, you're taking portion of the data set as well to establish those boundaries.
You're not learning the symmetry. It's like just take CNNs. Just take CNNs. Because there's a convolution operation, Dylan, you accept that CNNs are translation invariant?
Right. So from what you're saying,
yeah, that's all Changmin is saying. He's saying that when you give it a picture of a cat, you don't need to give it all translated pictures of cats. You can give it one picture of that cat. You don't have to give it all the translations because the model itself encodes the symmetry.
Yes, that's right.
So you're saying that given a specific learning algorithm, it's going to assume some form of bias towards a certain form of like boundaries for the separability of the data.
Yes.
So correct. Because of how it's already assuming some form of separability, you are getting something like a Venn diagram where that's your data sample space. Within those
your class boundary, you'll get a class boundary.
Right. Those there will be many pre-established, we call it pre-established circles. We know from
based on the training input, you will get different circles based
right.
on the different
now
classes.
You are trying to say that because as long as we put like for example labels in those circles, we know how to label those individual circles belong to certain classes based on the you learn the class with one sample. So it's essentially you're drawing like what I see on the screen, large circle inside a lot of circles, but we don't know what number that those circles are. But now because you provide the class with one sample, you can put like 4 or 6 over those smaller
correct.
circles.
In fact, actually, the training set matters a lot for the circles, because if we only have like 4 and 6, maybe the circle for 4 and circle for 6 will be very big. But if we have like another number like 5, then this will actually share the, let me use a different color. This will actually share the space in the manifold or in the latent space. You will share the space with them. And then like these 2 circles might be reduced because of the new class. So it becomes a bit more like specific. So all these classes are actually like competing for space in the latent space. So the more classes you add, the smaller these regions will become for each of the classes.
Yeah, but you need a good, you see, I think the confusion, Chungmin, is that to learn these circles is also called learning. And you're saying I'm not learning the circles.
You still learn in the training phase. It's just that after you learn in the training phase,
but it's not enough to stay. But it's not enough to stay one sample, or like it says you're one shot. I mean, this is not related to that at all, because you still need a lot of 4s, a lot of 5s, and a lot of 6s to learn these circles.
It depends on the invariances inbuilt in the model. So
Yeah,
theoretically, if you have translational invariance, you will learn all the potential translations with just one sample. Theoretically, yeah.
Yeah, but what I'm saying is you still need a lot of 4s to learn how to separate from the 5s and from the 6s.
I think that depends on a few factors, like how different are the classes.
Yeah, of course. Yeah, of course. It depends on the distance between classes and so on. But what I'm saying is that is what we think of as the learning problem. But when you write here, it seems to think that the learning that symmetry helps you need less data. It really doesn't. You still need to learn these circles, right? These circles are not given to you for free.
But because you know the one data point, and because your model interprets all the different variations. Okay, so maybe I can explain to you in the terms of a many-to-one mapping function. So assuming that we have a many-to-one mapping function, x, okay, mapping to y, right? Probably I can understand this, right? So if let's say I have a mapping function, maybe I have a function f, okay, that maps x to y. So this is like the traditional neural network problem where you have x as your inputs and y as your outputs. So if let's say you don't have the particular like symmetry, then it will be more like a one-to-one mapping, okay, where you actually have like this certain point, 1 point mapping to 1 point in y, and then you have another point mapping to another point in y. And so you need a lot of mappings to tell it that like all these different color circles here actually belong to the same class. So this is like if you don't have any symmetry, you need multiple mappings like this in order just to say that, okay, all these parts in X map to this part in Y. Okay, but what I'm saying is that if let's say you have a symmetry, okay, then what will happen is all these 3 will map to one single point in Y because of the symmetry. So
yeah, I mean, yes, I get what you're saying, but this is translations or this is let's say symmetry related perturbations of the same sample point, right? Like translations of a cat.
That's correct.
Yeah, yes. I mean, I know what you're saying. You're saying that an MLP, you have to feed it all the translations for it to learn. In a CNN, you don't. But I'm saying that's only one part of the story. To learn a cat from a dog, you can't use just one sample, symmetry or no symmetry. You need lots of images of cats. What you're saying is that from those lots, I can remove all translations.
But Prof, that's also because cats don't obey, like one single image of cats doesn't tell you all possible images of cats.
Yeah, exactly.
Correct. So I'm saying in this problem, assuming that your one input sample, by applying the different symmetries, you can get all your possible input samples for that class. Then you just need one. But of course, in real life problems.
So this is just that. Okay, so so this is how you're defining symmetry. Yeah. I think I get it now. I think we can move on. Okay. I think people didn't understand what symmetry meant. Yeah. I think it's what you said. From one sample, when I apply all the symmetries that I know from that class, I get all possible inputs.
Correct.
In that case, I agree. Yeah, you need.
In the real life data, it's hard to get all this, but we can reduce the amount of samples needed because we can omit certain symmetries in the input. Yeah. So if you model that symmetry or model that invariance in your network, like translational invariance, you don't need to do data augmentation to do translational invariance.
Right. Exactly. Yeah.
To learn it. Okay,
Yep.
so I'll move on. Okay, so actually that was the easy slide. So now this is the harder slide. Okay. Yeah, so in terms of symmetry, okay, now we talk about math. Okay, so this actually come from this math thing called like abstract group theory. Okay, but the idea is that you have a geometric domain. Like in this case, we have this omega as your geometric domain. So the geometric domain will be like, for example, in a 2D plane, it will be the real number squared. Okay, so this is like a 2D plane. So the geometric domain is basically where your input comes from. So if it's like 3D, then it'll be R cubed. If it's like okay, so I just test your, if let's say it's a tabular data with only one metric, like basically a scalar value, then what domain will the tabular data be? Anyone? So if your tabular data is from like negative infinity to infinity in value, what is the geometric domain?
1D plane.
Yeah, it will just be the 1D plane. Yeah, that's correct. Thanks, Dylan. So this is the idea of the geometric domain. So there's a transformation in this domain here that maps omega to omega. So basically this is a mapping that preserves the input space. So the range of your mapping or your transformation preserves the, rather the domain of your function is the range of the function. So it maps back to itself. So it's some form of like, if you know, the term is like isomorphism. Okay, but I'm not going to cover in detail what's isomorphism, but it just means that when you map a certain function, the output of that function contains the same elements as your inputs to the function. Okay, so one example for this is like permutation. So for example, you have the elements 1, 2, 3, right? And let's say I permute it in such a way that like maybe I just shift the row to the right. So if I map this into like 2, 3, 1, so like if in signal processing, we'll call all these elements the like code book or the code words or the alphabets. So as long as your mapping preserves like all the initial code words here is present here, then this is a valid transformation. Okay, so permutation is one of them. There's also Euclidean isometries like rotation, translation, reflection. I believe we shared some of this before. Like rotation in 2D is like you apply a cosine theta, sine theta to certain elements to do rotation. Translation is just add in a scalar to X and Y. Reflection is just maybe multiply by like negative something, or you can translate then reflect. Yeah, so these are Euclidean isometries. There's also this thing called diffeomorphism. Okay, it looks very difficult, but diffeomorphism actually is diffeomorphism in R squared in the 2D plane. Diffeomorphism is basically just doing a differentiation in that space. So let's say, so the diffeomorphism, if let's say this is like a mountain peak, the differential part should also preserve the smooth structure of your original peak. So this, in general, this is also a valid valid transformation. Why? Because after you do a differentiation in R squared, when you differentiate something in R squared, you will still get back R squared. And because it's a continuous domain, so it holds, this property holds. Okay, so that was a lot of math. Any questions? Okay, that's great. All right, also I forgot to say one more thing. There's this thing called a symmetry group. So after you apply this transformation G, okay, all such transformation G that can be applied that preserves the structure. Okay, very important. It's not just any transformation. Okay, it must preserve the structure. Okay, so actually what this means by preserving the structure, it means that, so there's this idea of, okay, I guess I have to introduce isomorphism. So there's this thing called homomorphism where you can map from one to another, and it can sort of like, it's a distinct mapping. But if let's say you can map from the output back to the input again, okay, this is called an isomorphism. So preserving structure means that if I map to the new transform domain, I have a way to map back to my original domain and preserve all the information that is present in there. So I lose nothing. So only if I lose no information at all, then this transformation, okay, is called an isomorphic transformation. All clear? Okay, so it means that I map to a new like rearrangement or new kind of structure, but I can actually map back from that new structure to the original structure using an inverse operation as well. Okay, so that is what I mean by symmetric transformation. And all these symmetric transformation belong in this symmetry group, big G. Okay, Dylan, you okay with this?
Yeah. As in classical neural networks are not isomorphic. That's what you're trying to get to, right?
No. I mean, yeah, if you map the x to y function, it may not be isomorphic.
Yeah, because you have no way of getting
Right.
from y to x again.
Right, because let's say classification, this will be like class, and this one will be input pixels. So you will lose a lot of information in order to classify. Yeah, so in order for it to be isomorphic, it must generate back the input space as well. But in this case, I don't need the neural network to be isomorphic. I'm just saying that in terms of applying the symmetries to the input, your different symmetries must be isomorphic, like a 6 on the top left. If it can be mapped to a 6 on the bottom right. And yeah, so because you can map like this, you can also map back to the original sample here again. So if you can do this, this will be an isomorphic transformation. Okay, I'll be moving on. Yeah, so initially I didn't put the slide here, but I thought this was quite important point, so I decided to add it in. Okay, I need to check where's my mouse. Okay, sorry, I lost the mouse in Zoom. Okay, I found it. All right, let's move on. So the symmetry group. So this is the properties of a symmetry group. So in this set big G, you have let's say you have two symmetric operations. Okay, one operation is called G and one is called H. It must satisfy these properties. Okay, so for all the assuming there's another T operation in this transformation, you can do a GH first that apply to T, or you do G and then you apply it to H3, HT, it would still be the same. It means that if I transform like so it basically means that if I were to have a particular sequence of transformations, it doesn't matter what I do first in terms of like, will I group this together or group this together. Okay, but that's it. Okay, there's also another special thing, it's called GH. Okay, it's not necessarily equals to HG. Okay, because there are some transformation, because actually the order of this matters. It's just that you can do this one first or do this one first. Okay, but the overall order of how you apply your transformation must actually be adhered to. Not always. I'll just put this, not always. Okay, then there's also this other property called identity. Okay, let me just write finish, not always here. So there's also this thing called identity. So in identity, it means that you have a unique transformation E such that it is like the identity transformation to your G, regardless of where you apply it, like at the front or at the back, it will still be G. So like for example, in translation, your E could be like the 0 vector. Like you don't even move at all. Yeah, then if you apply this field transformation, it doesn't matter whether you apply to the start or the back, it will still be the particular transformation here, G. So similarly, there's also an inverse such that you apply the inverse transformation, you still get back your E. And then lastly, we have closure. Closure means that if we have two transformations, G and H, G followed by H, or sorry, H then followed by G transformation must also be in the symmetry group. So this group is a closed group in math terms. So because it has all these properties, we can apply the symmetries and you can be sure that it will still be part of your symmetry group. Okay, so that was the math. Okay, now let's give an example of how this can be applied. So the group action is illustrated here. So assuming that you have X over here as your input space. Okay, so in terms of my X is basically this amount of pixels here, basically X. So X, okay, is actually applied to a particular domain U. Okay, and basically U represents like where you look for your picture. So like for example, this is U, and then U minus T means that, like, let's say initially U was here. Okay, U minus T means I look at this. So it just tells you where to look at for your original input. Okay, so there's this particular property for group action, is it means that if let's say you apply a particular operation G to your X, okay, to your input space, you do a translation. So initially the input is here, and then I translate to the right. Okay, it's the same as taking my initial input, okay, and then I undo the transformation in my in the transformation domain. So this actually is G inverse. And then if I like undo the original transformation, so every time I want to look here, this actually maps to this place here. So actually what you get is that even if you do the transformation to your input, as long as you do the inverse to your domain, you will get back the same. So actually this and this are actually the same. Okay, because you actually still look at the same patch, although you do the same, although you do the action to it. So yeah, this is a very, this property is just there to just say that your translation, when you do it on the domain, you can also do an equivalent translation in the input space X in order to get back your translation. Okay, this is a little complicated. The next slide hopefully is illustrating.
Changmin, can you go back? You have introduced some notation which makes no sense. Input domain, input and domain. What are these things? Why there's so many things? An X and a U. I understand G is your transformation. But what's X and what's U and what's the difference?
X is like your pixel space. The pixel space for like this beetle and the orange color pixels.
Okay, and what's U?
U is basically the entire universe of all pixels. So in U, you can also apply your like transformations on your U, and that will affect like how you view your image X.
But this, I'm sorry, this is very confusing. I mean, you have an input. I don't understand what you mean by input and domain. It doesn't make any sense.
So we have to see the next slide actually.
Okay, fine.
So you see, like, let's say I have an input tree, okay, and the input tree here, okay, originally the input tree was here, okay, but it's like translated up here, okay, using a symmetry group that translates this in the domain. So this domain is basically like, for example, in the input pixel, the domain will be a 2D grid of, it will be a 2D grid of R, because I mean, your pixels are from, okay, maybe your 2D grid is from 0 to 255. Because let's say your pixels are taking values from 0 to 255.
Yeah.
So in your domain over here, which is the entire 2D grid, we can map a particular transformation here, which is like a translation. And then by doing this translation here, okay, what it's saying is that if I do this translation, so this is a group translation operation, okay, using that particular symmetry, okay, and basically you can just treat it as applying like G to it. You apply it to your input, okay, it's equivalent to applying the inverse transformation, okay, to your, like, to how you read the, okay, let's say you have X here, you apply the inverse, and then you can like sort of like read this number here, which will be the same as.
Ming, you are labeling the tree, right? But shouldn't the entire thing be the entire input? The domain shouldn't it be the entire possible values that you have X in? It shouldn't be separate, right? Like what we are drawing, or it's just for pictorial.
Yeah, U here is just a particular point in your.
It's the entire set of possible
domain
inputs
here.
of X, right?
Yeah, U is being here, but I guess if U is translated to here, U prime, it also means that my X would also be translated. You can treat like this domain as like an external force that shifts your input. So if it like shifts one pixel to the top right, then your X also will shift one pixel to the top right. So this is like a meta force. How I view it is like this is a meta factor that controls your input. I mean, actually, to be honest, this is kind of hard to understand. But the idea is that if you apply your symmetry on your like your meta or your domain, you can apply the inverse on your signal part to recover the original image. That's all they're saying.
I don't know. My sense, my initial sense, if you don't mind my saying so, Changmin, I don't think this is hard to understand. I think this is made hard on purpose. Because even if I accept what you say, I'm still left going, so what?
Right.
You know,
so actually, this is not very important for the rest of the presentation. I included this here for completeness. Yeah.
Yeah, but I mean, maybe it's just that I think to say it's hard to understand implies there's something worth understanding. I frankly, I cannot, from what you presented, it does not seem like there's anything worth understanding here. it's not that I'm saying I figured everything out, but I've tried really hard to understand what you're saying, and I just feel like things just show up out of nowhere, right? Suddenly, so if you go back a few slides, you go back here to your when you say symmetry group. Okay, so let's say we go there. So no, go back one more slide. Yes. So this actually is the definition of a group. This is not a symmetry group. This definition of a group. Okay, and am I correct?
Yes, that's correct. But it's applied to a set of symmetries. So I call it a symmetry group.
Yeah, I mean, but I'm saying symmetry has nothing to do with this. This is definition of a group.
Of a closed group. Yes.
And you forgot to no, not a closed group, a group. A group by definition is closed.
Okay, can.
So this, so
that's
this is
correct. Yeah.
this is definition of a group. And what you forgot to mention is that the operation is what? Is it composition? So when you write GH, you actually are taking
Yeah, it's composition.
yeah, exactly. So the binary operation here is composition. And so GH means H followed by G. So when so you have this group of transformations, and within this group, like, or you have this set of transformations, and when you want to, for example, operate on two transformations, you compose them. And
yes.
yeah, and all it's saying is that composition has these properties. So I'm with you there. Okay, so now I have a group, but then now on the next slide, now I have no idea what you're talking about. What is input space and domain space, and so I get it that G, which is the operation, could be a translation of T units to the right. Why am I introducing input and domain? So like up to this point, we don't have that concept, and suddenly it's there. Why? I mean, you have input. I have an image. I can apply a transformation on it. Am I?
I understand what you mean, and I agree that actually the domain is not very essential to understand symmetries. Yeah, so maybe we can just treat this for info, and we move on to the next slide, which is more important.
Okay.
So this one, I think the reasons why the authors included this is because they did some mapping from like Fourier transform, inverse Fourier transform. Then this kind of makes sense because you have a domain and you have a signal. So you have a signal which is in time domain, and then you have like a frequency domain. So I guess this was intended for that purpose, but then the authors just use this to describe symmetries, which, to be honest, I don't think you really need this to understand the rest of the slides. But I just thought I include this because
actually, I think I figured it out. I just think the terminology is horrible. I think all they're saying is your input. For example, on the top, your input is an image, right?
Yes.
Okay, and I think what they're trying to tell you, you tell me if I'm right, they're trying to tell you that your input, which is a vector of things, of elements, those elements come from some quote unquote domain. So for example, if they're pixel values, like you drew before 0 to 255. So that's all they're telling you. They're just telling you that the elements of your image come from some like,
overall space that you take it from.
Yeah. So that's all you're saying, right?
Yes.
Okay.
So if you apply a symmetric transformation to your domain, it will affect your signals as well because your signals live on that domain. So what I'm saying that if I apply a transformation to my domain, I can recover that transformation in my signal space by doing the inverse of that transformation in the signal space. It is.
Okay.
It's quite intuitive, and if you think of it like if my translation affects both equally, then yeah, I can recover my original image by just like by shifting it back. That's all it's saying. Yeah.
No, but the values being in the set 0 to 255, you can't apply a translation there.
You have to apply the translation not on the individual pixels itself, but on the group of pixels.
Yeah.
So actually, I agree. This is like sort of intentionally made hard, like all math is, and there's quite a lot of math in the book. But I just presented this here because I thought this was for completeness on the symmetry groups. Okay, but I will touch on the important part. Actually, thanks for asking all this. To be honest, it took me 2 hours to understand this. I was looking through a lot of references just so I can understand this, because this is not a standard reference, or this is not a standard way to do it. Yeah, this was in the book, so I had to spend quite a lot of time understanding how this was done. Yeah, but yeah, I finally understood. Yeah, so I'll move on. Prof, if you're okay, I'll move on to the next slide.
Yeah, please go on. I think.
Okay,
it's
so
fine.
this is Rohan's pet topic. So remember, we spent about 1 hour talking about equivariance and invariance the last time. So let me give you the math formulation behind it now. Okay, so hopefully we will only take like a few minutes. Okay, but this is important because a lot of structures talked about later will use these terms, equivariance and invariance. So for example, I have a function, I apply a transformation group here to my x. So this transformation can be like a translation, like over here. So what is saying that if let's say my output is equivariant, I apply this to my input is equals to applying this same transformation group to my output itself. So let's say this is my output. In terms of a segmentation, is like the pixels telling you which is the cat and which is the background. So if I translate my original input cat, my output cat should also be translated equivalently, okay, because this network is equivariant. So equivariant is in some network architectures, like for example, using segmentation. Equivariance is actually also in the filters for the neural network, CNNs, because you use the same filter through all the patches. If let's say, let me just draw you over here. Let's say this is the input. The input has a number 6 here. And then if let's say I use the filter map, which detects like where are the 6s, okay, then my output should be something like this. Okay, supposing this is like a 2D 2x2 input grid, like that. So my output, assuming that I'm just looking for 6, my output should be like 1, 0, 0, 0. Assuming like 1 means that there's a presence of a 6 here. So if let's say I shift my 6 here, then this map will be 0, 1, 0, 0. So I can just apply the same shift that I did in my input to my output, and I get back this equivalence here. So this, it means equivariance. Okay, all clear so far? Equivariance, that's basically means if I do a transformation to my input, I can just transform my output and it will be the same. So this is a special case. Okay, it's a special case of what we've seen earlier of what we've seen here. Okay, it's because over here, this is generic for all cases. You will be able to recover back a transformation by taking the inverse in your signal space or in your input space. But for here, it's saying that I don't even need to take the inverse. Okay, I don't need to take the inverse here. Okay, I can just simply apply the transformation here. So this is a more narrow class, okay, where it satisfies this special property, okay, where I can apply the same transformation in both the input or the output space and I still get the same thing. Okay, this is equivariance, used quite a lot in CNNs. Okay, then we also have this thing called invariance. So over here we have this invariance term, which means that you actually, when you do a particular transformation to your input here, is equals to applying no transformation at all. So for example, my original input is a cat. If I translate my cat over here, what should my classifier output? It should output also a cat. So there's no change in the classification regardless of my symmetry group here. So that's why I say like earlier, if you like already know like all cats look like this, then you just need to like maybe translate the cat, then apply maybe scaling or rotation to the cat, and you still classify as cat. Then actually knowing just one sample of cat, if you have the corresponding network structure that can recognize all these invariant structures, you can group all these different versions of cats to the same output space. Okay, so I just pause here for a while. This is a very important slide. Okay, so any questions for equivariance and invariance?
Yeah, how does that relate to the symmetric structure of the network again? As in, I understand from what you are doing here for the two different equations, the difference is that for equivariance, it's you take the whole as a how do you describe this? You can assume one form of the composite function as an independent function to the next, right? But from what I understand earlier, symmetric structure in the symmetry in the structure is more related to invariance, right? Where regardless of the input, you get a certain output as your output x as your the output of the function. But how does that relate to equivariance?
So there are different things actually. Invariance means the output is unchanged. While equivariance, you still need to apply that same symmetry transformation in order to like make it match. So I would say that invariance is a more narrow class, okay, because you want this all to map to the same input. So actually you sort of lose some information here. While equivariance, actually your output still has some information of like maybe the position of the cat. But what I'm saying is that the way you process the data will be similar regardless of location in this case.
What is rho and G here?
A rho G is just a group transformation, a group symmetric transformation. So you can apply
What's
like,
G? Sorry,
G is what we saw earlier. So like G is this one here. G is this transformation. So rho G is just basically saying it is a transformation that is in this symmetry group. It's just a notation. Actually, I think
no, sorry, I'm just trying to figure out. You have notation, you have G and you have rho. What's rho?
rho just signifies a group operation. Yeah. So I think group operation just means that it is like a symmetry group operation here.
No, this is very confusing. Rho.
Hang on, go back
thing.
to go back to the slide again. Yeah, the equivariance and invariance slide.
I think for all purposes, like rho G is an operation that is on the group of symmetries.
What's F then?
F is just your original function that your neural network has.
What?
So invariance is a narrower definition of the overarching, which is equivariance. That's what you're saying.
No. There are different things. Invariance, you lose a lot more information because your output space is like many to one mapping. All your different permutations of all your different transformations here all map to the same output space.
Actually, Chungmin, let me try to explain to Dylan. I think he's asking a much simpler question. You're making a little bit too detailed. So Dylan, it's like the feature maps, right? If you have a cat, your CNN generates feature maps, right? If you shift the cat, the feature maps are shifted. That's equivariance. Do you understand?
No, not the feature map. The output of the feature map.
No,
is shifted.
the feature maps are shifted. That's equivariance. That's translation equivariance. And translation invariance is the final output of your CNN, is that it's a cat. So whether you put in a shifted cat or a non-shifted cat, you want the output to be a cat.
Yeah, so I mean, if you look at like patches, you will see that the cat that is like over here corresponds to the cat silhouette over here. Similarly, if you apply a transformation like maybe a translation, you'll see that this cat appears here. So the way you process the cat will be independent of where the cat appears in your input. So this is translational equivariance.
Yeah, so the feature maps are shifted.
It's a more relaxed way of like processing data because you don't need the output to be same regardless of where this is. So it's used for particular kinds of problems like segmentation. Whereas for like classification, regardless of where the cat appears, we still want the output to be the same. So this invariance thing is like used for classification.
Okay, so
yeah. So Prof, back to your question on rho G, right?
So there's so there's four variables here: X, G, rho, and F. Just tell me what they all are because it's
okay. So we start with F. So F is basically your original neural network function that maps inputs to outputs.
Okay, so F is the neural network. I can get that. Okay, fine.
So X is your input.
Yeah.
So X is a subset of all possible input spaces X.
Okay, yeah.
Okay, G is your transformation that maps the omega to omega, which is your all potential input spaces.
Yeah.
Okay, and rho G basically is a group. They call it a group action on G. So I guess rho G is basically like maybe just any G that is in big G. Yeah, I'm tempted to say that this can be equivalent to G, but
Yeah, I
I'm
was
not.
gonna say, what's rho?
too
No. So you told me what rho G is, but you didn't tell me what rho is. Are
Yeah,
you
so
saying it's just
rho
another?
G is a group. They call it a group operation on G. So I'm thinking it might be like a way to transform your original G to other G's that still exist within the group structure, big G. So
Okay.
for all purposes, I think you can just replace this rho G with G and this will still hold. So you can,
By some G and G, yeah.
yeah, you can just replace rho G with some G in G, which is basically you can replace this with, basically
Yeah.
you just take away the rho. Yeah, and I
Yeah,
think
yeah.
this will still work. Yeah.
With that, it makes sense to me. Yes.
Correct.
Yeah,
So
I
I
mean,
also no idea why the authors needed to use a group action. There might be some intricacies in it that I'm not aware of, but I think for all purposes of our discussion, you can just assume that there's no difference between rho G and G.
okay, yeah.
Okay, so all clear so far? So this is the most demanding math part so far. Okay, thanks for the questions, by the way. It really helps with our understanding. Okay, so let me just give you a picture by Hinton. Okay, this was his part-hole network or hierarchical network that he did. So is equivariance or invariance good, like at all parts of the network? I mean, if it's so great, you can just apply at all levels of your network, like your CNN, starting from your first layer, you start applying all your invariances. So Hinton just gave this example to just show that, you might want your whole phase to be like rotational invariant, right? Like you want this and this to still be interpreted as a phase. But do you want to apply it at like the feature space level? Like if you were to like rotate your mouth and then you like maybe rotate your eyes like that, yeah, you may not get what or even the nose is actually rotated. So it's actually all rotated like to the right. So you can rotate it back like that to get back your face. So if let's say we rotate all these different parts, okay, you might actually lose the whole meaning overall, because you lose out the like part-hole relation if we rotate too early. So what it's saying is that while invariance or equivariance can potentially like help reduce the number of samples you need to train your network, you should only apply it at perhaps the last few layers, because if you care about the part-hole relations, okay, you do not want to like do this kind of invariances too early that might make it lose certain information. Okay, so this is just a caution. Okay, so yeah, I just put this slide here just to say that while invariances and equivariances may be good for your for your network structure, there's some caveat to it. Okay, it may not be good at the early layers. Okay, I'll be moving on. Okay, so now we start with the first structure that we will analyze today. So there's like 3 CNNs, GNNs, and actually there's 4, then transformers, and the last one will be reinforcement learning. Okay, I may not have time to cover all, but we see how much we can cover. Okay, I don't really want to rush this. So yeah, maybe if need be, we can spill over like next week a bit. Okay, but this is CNNs. So translational invariance equivariance is applied in this. So what is translational like equivariance? So we saw earlier that if we apply a transformation, a symmetric transformation to your input space, is equivalent to like transforming the output space, applying the function and then transforming the output space. So it is very similar here, because like you have a certain function like that you want to apply to your input space. So regardless of where my input patch is, okay, if I were to translate my input patch to the right, then it's equivalent to like translating this input patch to the right again, like that. Yeah. So CNN filters the operation of this convolution here, where like this C theta is my learnable filter, the filter weights. Like over here, this is a binary filter, like 1, 1, 1, 3. This is a very like math way to represent CNNs. But the idea is you apply a certain filter to your input space X, and then you do like convolution operation like this. This should respect translational equivariance in the sense that regardless of where my image appears, like I would still be able to classify them in the similar way, regardless of location. Okay, all clear so far? Okay, so this is the convolution operation described in math. Okay, the first part is just the way to like apply like the filter to the output and then some normalizing factor. Okay, in 2D convolution, it just means like basically you just treat it as like your x multiplied by your filter. So this alpha is your filter. Yeah, so this is basically the usual convolution operation that we see in GNNs. Okay. Okay, so this is the way that in geometric deep learning, how they represent like a CNN function that can be expressed in terms of like more broad general functions. So over here, this is an equivariant linear layer fx. And fx is like the same as your like convolution that we saw earlier with shared weights. Okay, this sigmoid here is the non-linearity. Oops, this sigmoid here is the non-linearity. Okay, and then lastly, we have this P over here. So this P here, they call it the cosaning operation. Okay, but I mean, in CNN terms, this is more like a pooling operation. So firstly, you will see that like the translational invariant global pooling. Okay, what this means, this deserves some illustration actually. So for example, if I use like max pooling, so if I max pool this particular filter here, like 2, 5, 3, 1. If I max pool, I will get like 5, right? So let's say if I were to like do some like shift of my input such that like maybe my 5 appears here, and maybe 5, 1, be 2, 2, 3, you will still get back like 5 here as output. So because the various transformations of an input give you the same output, so this is like translational invariance. So local pooling, which is basically non-global pooling, like if you do like pooling of 2 by 2 that is like applied to the image, actually this translational invariance may not hold, because if you shift your image a bit, your different outputs might actually change. Okay, but at least to the local level of like, if you view this patch as a local level, at the local level, doing pooling actually helps with maintaining some form of invariance here. So actually pooling is a unique thing to CNNs, because like maybe the input space has been over parameterized, like it's too high resolution for like a particular purpose like classification. Okay, but later if you go see like GNNs, graph neural networks, actually pooling may actually harm performance, because if you have nothing to like go to a more like broad resolution, if let's say going to that broad resolution or coarser resolution actually like takes away important information, then actually this pooling thing is not very good for your network. Okay, so just treat this pooling with a pinch of salt. Okay, it's useful only in like probably CNNs, because I think the image has been over parameterized. Okay, but what's more interesting about CNNs you can take away is this particular F here, which means that it is a shared weights for the filter, and hence it is translational equivariant. And this translational equivariant really helps it a lot in terms of like learning all the possible inputs that can just vary by translation. Okay, so this should be quite common knowledge. I'll just move on. Okay, so there's this very interesting discussion about data augmentation that they presented. So I would like to like touch on it a little bit more. So,
And can I share some thoughts?
okay, yes.
I think the reason the group action is there is because you have a group, you have some input, and sometimes it's not clear at all how the group elements operate on that input. In your case, when you said it's transformations, it's very clear. But when it's not clear, then you have to define how the elements of your group act on your input.
Okay.
And that's the group action. So you kind of get it, right?
Yeah, it's a set of actions that can potentially be applied. Like,
Yeah, it's
just do for one action, because it may not lead to the inverse mapping being present.
Yeah, no, I mean it's the way that the group elements operate on the input for general groups. I guess in your case, since you define the group to be things that already like translations, it's very clear how a translation operates on the input. Right?
Yes.
But,
so translation,
but for example, let's say you had translations, right? Does your translation wraparound?
No.
Yeah, but let's say you wanted it to, then you could define that in the group action, because the group action takes a group element, it takes an input, and it gives you, it takes something in your input space, and it gives you something back in your input space, right? It's a row of G is the group action, operates on the input, and it gives you something in the input, which is why then you can run your F on it. So in your case, if you wanted a wraparound, that would be defined inside row. Row would, yeah, whereas G is just a translation, right? If you wanted to just
So
flip,
the row will give it a wraparound effect because
yeah,
of
it
the
defines
function.
how does that group element operate on your input X. Yeah, it just happened when we think of translation, we have an intuitive idea of how the translation operates on the group element.
That's true.
Sorry, on the input. But G can be arbitrary group. It doesn't have to be translation. It can be something that you may not know how it operates on the input. And the group action tells you how it operates on the input. So like this row takes a group element, it takes an X, and it gives you another X.
Yes.
Yeah,
Actually,
so
that makes sense now because like maybe your G alone may not be able to specify how.
yeah. And the simple example is, do you have wraparound or not when you translate? You might want it, you might not want it. And so that cannot be part of the translation function. It's part of the group action thing. Yeah.
Okay, thanks, Prof.
Yeah, no problem. No, this is bugging me. So I went and I read up, and this is just, it's a standard thing in group representation theory. Yeah, I mean, people talk about like this group action as part of, yeah. Okay, thanks. Yeah, please go on.
Okay. So I will talk on data augmentation. So, you know, for like ImageNet, you actually need to do quite a lot of augmentation for it to be competitive, like rotation, scaling, shearing. So actually I found that like, for example, Cypher 10, without like doing the data augmentation of like some form of random cropping and like horizontal flipping, actually the performance drops by about 10% in terms of accuracy. So actually data augmentation plays a huge role in performance in like Cypher 10 or even in ImageNet. So why is this important? Okay, because you see, translational equivariance is already taken care of in the CNN network. Okay, but it does not have like color change, rotation, scaling inside because the filters just don't do this kind of thing in a native network. Of course, if you build like multi-scale networks, you can get the scaling out. You do group transformations, like what Rohan did for like his rotational CNNs, you will get all this also, rotation. But in the native vanilla CNN, you don't actually get all this in. Okay, so what people have done is that you actually, it's like a cheating way, or rather it's a way to get the performance without changing the network structure too much, is they actually use data augmentation in order, okay, to like let the network know, like, let's say this is your input, it lets it know like what class to map into. So with data augmentation, I can give it, it's still not going to be a one-to-one mapping, many-to-one mapping, it's going to be a many-to-many mapping, but at least the many-to-many mapping falls within the same like manifold or latent space, like as you see over here. Okay, but over here, this is using, this is actually using data augmentation to do it. So you may not get the same mapping in your manifold space, okay, or your latent space, okay, because you don't have all this like rotation scaling built inside your network. Okay, but using data augmentation can help to alleviate the problem a little bit. Okay, however, it is actually suboptimal in terms of sample complexity. So let me just give you an illustration of why. Okay, so let's say we want to like separate, we want to do certain invariances. Like let's say we have invariance 1. Okay, so in order to do invariance 1, I need at least 2 samples, right? Because I need to tell the network like translate left, translate right. What are my possible inputs? Okay. So if I want to do like invariance 2, I need at least 2 samples again. So if you want to do like all invariances, like all possible combinations of it, you can see that is like, let's say we have until invariance n. Let's say all in, so we need at least n to the power 2 to the power of n. samples. Because like, let's say, for example, you need 2 samples to differentiate each invariance. If let's say you have like a high dimensionality, you need to apply this like translation invariance in your X, your Y, your Z, your 4th dimension, 5th dimension. You need like at least 2 samples in each dimension. So of course the math is not so simple, okay, but I think this sort of illustrates the problem of sample complexity scaling up exponentially with increasing dimensionality. So data augmentation actually is not very good if you have a high dimensional data set. So I think Yan LeCun also mentioned this. I mean, in my last presentation on the autonomous vision for AI, he also said that like he felt contrastive learning was not the way to go. And actually I realized why. It's because in high dimension, if you want to use contrastive learning, you need at least 2 samples to say this is in the class, this is not in the class. It is going to scale up exponentially. And let's say if you have 1,000 dimensions, you can't possibly have 2 to the power of 1,000 samples. It's just too much for current compute, and it's very inefficient. So if we could enable these symmetric structures inside the network itself, actually it can help to solve the curse of dimensionality because you don't need that many samples to augment. I think this is quite interesting because yeah, I think this ties in a lot with what Rohan did for his scale and rotation invariance network the last time. I think this is something that we can look into for like other network structures as well. Instead of augmenting the data, you incorporate that into the structure, and it actually can help to reduce the sample complexity. Okay, I pause here for a while if you have anything to add. Y'all agree with this? I think this is something quite interesting. Yeah, I've been wondering about this also, data augmentation, and this actually seems to make quite a lot of sense to me. Okay, if no...
Why was it interesting again?
Oh, because it just shows that data augmentation is like a stopgap kind of measure. It may not scale up very well. So, you know, transformers, we actually use like mass language modeling as data augmentation. Actually, that also doesn't scale up too well because anything that is not incorporated in the structure of the network won't scale up very well. You will need a huge running time in order to like implement all this. Like AlphaZero use self-play as data augmentation. So if you don't build certain structure invariances in your structure of the network, you're going to need a long time to train AlphaZero, which is what I face when I train my AlphaZero. So I can fully understand the point that data augmentation is sample inefficient. Dylan, do you have any comments on this?
No, okay, so I wouldn't dispute that, but I guess it also depends on what kind of augmentation you're doing and why you're using it. So the main, from what I understand, the main reason why you use data augmentation is if let's say you have like all the samples are some spot in a plot, right? In your data sample, you're not going to have access to the entire samples in your problem space. That's not possible. It's too much data you're supposed to cover. So what data augmentation does is if you're trying to fill the gaps, is just to provide more crosses across the gaps that you're not looking into the problem space, right? But there is another way you can do augmentation is regardless of what input you get into your model, you try to make sure that the input looks something similar to what you train a model on. Then in that case, I think data augmentation is still relevant. I guess for problems like images where because of how we are processing the image through a CNN, the complexity for each samples are very large. So you can see why data augmentation, it's really hard to perform well there. But let's say for even like Sci-Fi 10, it's like for example 32 by 32 pixels, you get a scale up version of Sci-Fi 10, but if your augmentation somehow is able to make it look similar to what you train the data on, then it works quite kind of good. So there is no problem of sample, there is limited problem of sample complexity there.
If
so I wouldn't say
your,
that data
dimensions
augmentation
are
is
not-
totally like not.
If your input dimensions are small, then yes, you won't have that big problem. But if we scale up to like higher dimension images, then yes, there will be some issues.
Yeah, that's what I like to share. That's all.
Yeah, thanks, Dylan. Yeah, Rohan also mentioned a similar point in the chat. Thanks, Rohan. Okay, I'll move on. So actually try to avoid data augmentation if possible. If you already know that there's this invariances that exist in your data, like translation or rotation, I think somehow doing something to do with like the constellation space of the signals. Yeah, if you already know that it's rotational invariant, yeah, add it into the filters. It will actually probably help the model classify better. Yeah. So okay, this is the point. Okay, modeling other invariances into GNNs. So this diagram is just a math way to represent like certain rotations in a cube. Okay, there's like a total of 16. Can't remember how many operations there are, but basically there are different equivalent rotations or reflections of the cube. Okay, so oh sorry, this is just rotation. This is a rotation. Okay, math is the rotation group OH. Okay, so if we already know that certain symmetries or like invariances are present in the data, you can actually put that operation into the filter itself, and perhaps it will be able to like model these invariances well without you doing data augmentation. So for example, one you can do is you can do a rotational transformation group here, and you apply it to the filter. Yeah, so this will actually help to capture all possible rotations of maybe like the number 6. You can like, assuming you have the number 9, you can like potentially rotate it like in different orientations. And then your filter can actually just based on one orientation and can classify it as a 6. Yeah, so all these are equivalent like this. So yeah, you can just apply this transformation group or symmetry group operation, okay, to your filter. And as what was mentioned earlier, maybe you want to do this nearer the end of your network. Okay, you all can remember why? Because if we look at this part here, like what Hinton mentioned, if we were to rotate too early, maybe we lose some semantic meaning between like the parts. Okay, so maybe this, so I mean, contrary to what Rohan did, where he did like this symmetric filters in every layer of the network, maybe this can be done like at the last layer only. So this is something that we can look into, okay, in order to like reduce sample
Wait,
complexity.
who said that? Hinton, is it?
Hinton, yeah, part in a, I think it's called a part hole paper.
He has explicitly said you put it at the end is better.
No, I mean, you can look at he didn't exactly say it, but he's just saying that if you rotate the intermediate layers, you might lose information. So if you gather what he said, it means that you probably should only put these invariances at the end. I mean, that's
No, I disagree with that statement.
All right, what do you disagree with?
I think it shouldn't be like you focus on any of the portion of the layers for this. If you want to incorporate some form of invariance, it should be you should delegate some portion of the responsibility across the model, so that you don't have sudden like one layer you focus all your strength into, then somehow you hope that it carries on towards the end. I think if you're thinking of as model as some form of like data processing layers for each of the subsequent intermediates, right? Each layer should be responsible to some degree on how you want to incorporate invariant functions to your input. So it ties in, I think, with what I discussed with you and Rohan, that I'm trying to look at a way that the, how to say, you process information at a gradual scale across the model. I think
Right.
that's what I'm
That's
getting at.
also provided that
I don't think Hinton,
you
did
don't lose
Hinton say
semantic
that though?
information if you do this invariance too early. Like over here, if you look at the face, if you rotate the eyes or the mouth too early, you won't get like the right structure at the end. So
No, but even if you focus at the end or you focus on an arbitrary layer, right? Because of how neural network is structured, the subsequent layer, what you give the subsequent layers of
yes,
input
yes.
gets affected prior to that, you
right.
see. So
Then
you can't just focus on one layer of this.
what you said is actually correct. So actually there's this structure of network called equivariance network. Okay, where you have like this is layer 1 and this is like layer 2. This is the original neural network. So actually what you say actually makes a lot of sense. Okay, so I like to correct what I said. Okay, may not be at the last layer. Okay, but any layer that you deem fit, you can apply this transformation here. So you can apply your rho G, your transformation to any layer here. So you will have another network here. Okay, let's use a different color. You have another network here called the equivariant network where basically we take into account that equivariance study. So assuming we only apply this one time, okay, so actually you are right. It doesn't really matter whether we apply it at the start or at the end, as long as we only apply it like once, okay, then you won't have the possibility you will get all this. Just like, let's say if you rotate your eyes at the beginning already, everything will be rotated the same way. So you will still get back this whole face. Okay, so you're right. So at any point of time to get, so this is like the output. So at any point of time, we can actually apply the equivalent function here to get to our equivalent network from our original network. Is this what you're trying to say?
No, not really, but continue. Maybe I'm getting you wrong.
No. So it means that you can not only apply it at the last layer, you can apply it like at potentially any intermediate layer. As long as you only apply it once, it's equivalent to like taking like maybe this path on the, it's equivalent to like taking this path in the network. Yeah, so ultimately you still model the equivariance in the network. But you can model it early or model it late. As long as you don't apply it like twice, you won't have the case where you rotate the eye one time, then you rotate like the face another time like that. Yeah. So yeah.
Why don't you apply more than once?
Because if you apply it more than once, you might end up with like this part here that gets rotated like out of portion.
No, why would that wouldn't happen, right? When you apply to a specific layer, you're observing just a snapshot of what's being processed across the model. So if you apply it more than once, it's not saying that it's a compound effect to a specific input. Because each snapshot of your input as you process across the layer conforms to one representation in the manifold. So as long as your loss function for that specific snapshot is, I would say, kind of similar across the what you're trying to apply, even if you apply multiple times, you shouldn't get a case where, like you described, you will kind of rotate the parts.
I guess Dylan, assuming some sort of segmentation is allowed here. What you're saying is when there's no segmentation, then this cannot happen.
What do you mean by segmentation?
That you can get the eye separately from the nose, from the mouth. Right. Segmentation would be you would segment these quote unquote objects.
So some portion of the input from the prior layer gets processed differently from the separate of the portion, is it?
I mean, if you allow segmentation, what you're saying is that as long as you don't allow segmentation, this can never happen. And I think that's true. I think that's true. But I think in this diagram, maybe Chongmin, this is, or this diagram, whoever drew it, is allowing for segmentation. And when you do that, he's saying you shouldn't apply it at all levels because you might get things that are inconsistent.
Oh, okay. Then I agree with what both of you are saying. Yeah, it's possible.
Right. So actually, it depends on the kind of data you're dealing with and like at what level are you segmenting it, as what Prof mentioned. So yeah, so this is the network that I was saying, the equivariant network that some people have come up with, that you can choose when to apply your equivariance, but you only apply it once. Okay, so that you don't have the situation where you rotate the parts like that. Yeah, so it's like a one way from left to right. You don't go back to left again.
No, I don't think it's the reason why you get that is if you do some form of like I think what Praveen who said the segmentation, right? Like you don't have the entire data being
so
as
this
a whole.
network allows for segmentation because this is like the part level and then at the top is the whole level.
Oh, as in exclusive to what Hinton was proposing.
Yeah, correct. So this is the solution to Hinton's problem that he posed. Some people have come up with, I forgot who was it. This is called equivariant network, where you only apply the equivariance transformation one time. And you can apply at any level, but you can only allow for one time crossing from left to right. And this like helps to preserve the overall relation between the parts. Because whenever you do the equivariant transformation, you transform all the parts similarly.
But then that shouldn't be, maybe it's because the title of the slide is a bit confusing. The context is it's only for, right, assuming the case where segmentation is an issue, right, for like what Hinton was
Yes,
trying to
yes,
do with
yes,
part
yes,
whole.
correct,
But
correct.
here is saying applied at all levels of network. I am assuming like for a generic CNN as well.
Yeah,
And
no,
I work with a
generic
CNN and I introduce like
generic CNN has part whole relations because at the base level is like the feature level.
you do this for a generic CNN, it still works.
Depends on what equivariance you implement. Yeah,
Okay.
so I think it's a use case specific, but this is just a caveat. Okay, so let's move on. Okay, so I'll maybe just touch on graph neural networks and then we just end maybe another 15 minutes. So graph neural networks have this thing called permutation invariance that what Prof asked earlier. So I'm going to cover this in detail. So firstly, let me just introduce. So if there are n nodes in the graph, there's an adjacency matrix of n by n. Over here, like maybe this black color means that it's a 1. That means there's an edge connecting from like, so let's say if we look at this is like node 1, connected to node 1, connected to node 2. So like node 1 is connected to node 2. Node 1 is also connected to node 4. Node 1 is also connected to node 6, 8, and 10. Yeah, so you can see that this like specifies the connection for all nodes. This is like node 2 connected to node 1 and node 3. So you can see node 2 is connected to node 1, node 3, and also node 6. So this is the adjacency matrix. And also in popular deep learning fashion, we have a vector for each node where we call it a feature matrix, or you can call it like the input dimension. So this input matrix have dimension D. You can specify it for n different nodes. So this is dimension n. So X is your input space. So overall, this is determining the edge connection, and this is determining the nodes, which is your vertices. Of course, there's also a possibility that you have edges, or you have this edges here that can contain another vector information here as well. Okay, but we're not going to look into that because that's a bit complicated. Okay, you can actually also have meaning in these edges as well. Okay, but for now, we just assume that the meaning is all in the nodes. Okay, and then the edges are there to just connect the nodes. Okay, so all clear so far with the graph structure.
So can I check with you, Chungmin? So a graph like this is actually one data point.
Yes, that will be like your input data.
Haha. So this was the bit confusing to me. Okay, so now I think I understand. I think my question from before is answered. But anyway, please continue. So this is one data point, one sample.
Correct. So
because each of these, what you have in this example, you have 11 features of dimensionality 4. So each feature has like 4 is of dimension 4, and there's 11 features, and the edges determine the relationship between the features.
Yes.
And so this is actually, yeah, the key is, you see, sometimes they use graph neural networks in like social media and like a community learning, and they draw graphs like this. But in graphs like this, each of the elements is a data point, is like a person, and this is the social media connection is the edge. But
sometimes the data is illustrated in the edges. In the edges, exactly. In the social media network, the adjacency matrix is the main information.
Yeah, exactly.
This may encode the most important information in a social network.
Yeah. Okay, great. Thanks. So I think that's, wow. This I guess I've been misunderstanding this for a long time. So this is actually one data point.
Yes, this is one data point.
And you might actually have, if you have a million data points, you have a million of these graphs.
You have a graph with a million nodes. I mean, depends on what you mean by one data point. So if let's say one data point is a person, then each person is represented as a node or vertex in this graph. So you can have like 1 million vertexes, but you still have one set.
That's not what I mean. No, I mean here, like am I correct? There are n features, right? Each feature is of size D, and the adjacency matrix connects the features to each other. So this is like one data point. And if I have 1,000 data points, well, each of them is a graph. So I have 1,000 graphs.
Okay, so you probably are treating an entire graph of adjacency matrix and feature matrix as one data point.
Yeah, isn't that what you're saying here? That's what it looks like here, right?
That's
here n is number of features.
That's only if we have like time varying input. So you can treat this as, you can model like graph neural networks in an RNN way, where you have this as your time 1, then you actually like you can actually like do RNN style, and then you can map to another graph time too. Yeah, but for most use cases
No,
for
no, I don't mean
RNN,
RNN. I mean, what I
for
mean
most
is
use
that,
cases of RNNs, you actually just only have this one time.
no, I mean, forget RNN. It seems to me like you could just have a data set of n features and the features are connected to each other. So you have an adjacency matrix. So now you should connect the features to each other and the edges connect the features to each other.
Yes.
Yeah, I mean, there are n features here, right?
Yes.
I mean, each data
And
point,
nodes with each feature with d dimensions.
yeah. So there are n features, and I could like in a tabular data set, I could have n columns, right?
Yes,
And those
yes,
are n. I mean,
correct.
that n matches the n features here are like the n columns of my data set.
So maybe in a tabular data set, what we will have, as what I mentioned earlier, is that we have unconnected nodes because maybe the data don't connect to each other. There's no relation at all. So it could be like nodes with no edges. So
Right, but these nodes are not the data points. These nodes are still the features.
these nodes are the individual like tabular data. If we talk about tab data, this could be like age. Then this one.
Yeah, exactly. They are the features, correct.
Yeah, correct. This one could be like heights. Yeah, and
Right,
so
right.
on.
And then so the set of these forms one data point. Just
Yes,
like
yes.
one row in the tabular data forms one data point. What's interesting here is that when the features are correlated, you can do this. For example, Danyang, when we wanted to run SHAP, we like one in the original SHAP algorithm, one makes the assumptions that features are independent, right?
Yes.
But when features are dependent on each other, right? Then you had one way of doing it by coalitions and stuff, right? I mean, you had one way of dealing with that, but this is another way of dealing with it. Just take the adjacency matrix
You can connect them like that.
and just encode, say, okay, this feature is connected to this feature. So I'm curious, like maybe this is something that could be of interest to you, is if you could form an adjacency matrix that connects the features that shows the dependence, then perhaps one can do like SHAP analysis on this.
Yeah. Anyway, I'd like to just say that, let's say if you have like multiple samples for each of them, actually it's possible to represent your input dimension in a 2D form instead of just single D.
Okay,
you can have like, so that you can apply maybe like convolution operations on it.
Right. I see.
Yeah, so you can do something like this. I mean, my drawing isn't that great, but I hope you can see that this is like a 3D block.
Yeah, exactly. Yeah.
It is possible to do like 3D. You can do whatever convolution operations you do over here in GNNs.
Yeah.
Graph neural network as well. So the operations I will show you later in the next
Okay,
slide.
cool. Thanks.
I wanted to add on about the point about the adjacency matrix. So I do agree that it is interesting, but I was just wondering whether the adjacency matrix is learned or is it like self-defined?
Okay, yeah, that's a very important thing. So for most use cases right now for graph neural networks, the adjacency matrix is already defined. Okay, because it is I think it's an NP-hard problem to actually find out the latent space of the adjacency matrix. Basically, find out the connections, then use the connections for. So it's like neural architecture search. If you want to do both at the same time, you have conflicting output loss functions, because one loss function will be for the structure and one loss function will be to feed the data. So some people have come up with a two-step approach where first you learn the probable structures using some Bayesian approach. Then after that, you use that learned structure to actually then process the data. So it is an open field right now in terms of like how to the network to fit the adjacency matrix.
Yeah, I mean, it's kind of like one way to think about it is it's domain expertise, right? Comes in and helps you with the adjacency matrix.
I guess it's a bit troublesome if we were to, the thing is domain expertise only works at a data set level. So at an overall level, we know how features relate to each other. But from what I'm seeing here and what I'm understanding, this seems to be at like a per sample level. So you have to define for each patient what's the relationship between the features. So this seems a bit difficult.
Chongmin, can this adjacency matrix change for every sample?
For every sample, it can.
Oh, that makes it very hard. But
usually, if we have tabular data like this and you want to do in a graph, I don't think your adjacency matrix will change for every sample. So you can fix it also.
Yeah, Daniel, I think in a like medical scenario, this would capture medical knowledge. So it will be fixed. Yeah.
Yeah.
In
Yeah,
most use cases for graph neural networks, the adjacency matrix is fixed.
Okay, cool.
I see. All right, thank
Okay.
you.
So let me just show you the permutation operation. So we can permute both the rows and the columns. Later there will be a slide to show the math behind this, the row and the column like that, so that like you can arbitrarily number your nodes. So this will be down node 2, the initial node we had, and then node 2 connects to node 1, 4, 6, 8, 10. So you can see that we have reordered the connections as well as the initial node, but the adjacency matrix actually is the same. So if you look at this graph and the graph that is before, right? Although we have done the permutation, you can see that actually the graphs are isomorphic, because like isomorphic in the sense that I don't lose any data at all. Because if we look at the previous diagram, you can see that this like node 2 is also connected to like, you can see that it's similar connections. See, the slide didn't change much. The blue color connections are the same. It's just that the node numberings change. So this is a very cool feature, is the sense that if you do some permutation, you can guarantee permutation like equivariance, because like you do some permutation, but the way you conduct the operation across the input nodes will not be changed. And this is also why graph neural networks are quite good, because like let's say you have a new feature here, feature 12, and assuming you know the connections here, even without training on this input feature 12, I can actually get my operations to work on this new node 12. Okay, because the way that the graph neural network is trained, at each step that you do your operation on your nodes, you actually do the same operation on each node. So if I add in a new node like that, my graph can handle it. So some use cases for it will be like, if you were to calculate the sum of 3 numbers, right? So if your neural network is calculate sum of 3 numbers. So if you want to do like a normal CNN, you need to like train this to calculate with 3 inputs. Then let's say if I want to change the input, calculate sum of 10 numbers. Okay, for MLP or like CNN, you cannot just go like that. Okay, but for GNNs, because of the way that the operations are node invariant, you can just add in more nodes and then you can still compute it in the same way. So in GNN is a zero-shot learning to extend the domain, to extend the number of input features. Yeah. Okay. So yeah, I hope this shows like how powerful GNNs are. In fact, actually, I think GNNs, I'll be working on it soon. Okay, because I feel like GNNs are the next big thing in AI. It's already growing to be quite big, and I think there'll be more and more people who will be interested to research on GNNs, because it is like, you know, in string theory, you have like the theory of everything. So GNNs are like the graph that can fit like all previous architectures. Yeah.
I still don't get how this relates to symmetry in the structure though. It's just one form of symmetry, which is permutation invariance, right?
Yes.
So why is it more powerful than, let's say, if you are working on like image data compared to CNNs?
Yeah, so if let's say image data, if the way you handle the pixels and the neighboring pixels are the same, in like traditional CNNs, you have some limitations in terms of your input size. It must be like sort of a fixed size in order to perform the same operations. But for GNNs, because the way you apply it at a single pixel is fixed regardless of the number of pixels, you don't need to train the GNN specifically for different input sizes. They will still learn the same inputs. I'm sorry, they will still learn how to fit regardless of input size. Because
but you can always pre-process an image for the CNN as well,
yes,
right?
yes, correct. So in cases where you have difficulties pre-processing, like for example, calculate sum of 3 numbers versus calculate sum of 10 numbers, if your operation per node is going to be the same, GNNs are very powerful because they generalize to any new node, provided you know the adjacency matrix. Okay, so I don't think you can understand this right now because
No, but the adjacency matrix is already pre-established, right? So that adjacency matrix is for that particular problem, which is calculate the sum of the 3 numbers. That means if you want to generalize to sum of 10, shouldn't it be a separate adjacency matrix?
you need to have domain knowledge about how to generate this adjacency matrix for arbitrary numbers. Then you can do this.
Dylan, I think the thing that they're taking advantage of here is that this adjacency matrix is sparse, typically. So this graph is not a fully connected graph. I think if it's a fully connected graph, then you lose all the benefits that Chongmin is talking about. But
actually, it can be fully connected as well for GNNs, and it was
it can be, but but then adding a new node.
Or it will
doesn't
still be
give-
okay because then your adjacency matrix will be fully black. It will be like one transpose, which means that it will
Yeah.
be connected to everything.
Yeah, I know you can formulate it, but you lose the advantage. You can't pre-compute things.
You can add in more nodes, like from 3 nodes to 10 nodes with a fully connected graph as well, assuming that the operation per node is the same.
Yeah, but it's not, right? Because it's fully connected. So whatever new things you add get added to every node. So the computation load per node increases linearly as well. So
That's true. That's true. Actually,
I mean, my gut feeling.
Okay.
Anyway, I haven't done this, but my gut feeling is that you're taking advantage of the fact that there's local connections. Like for example, node 2, like it's connected to a few nodes, not to all the nodes. And so if you add something, you just need to figure out what nodes it's connected to, and you can just incrementally update. And all the other
Yes,
things.
actually that's a key factor because graph neural network takes into account the structure of the connections, which is
Yeah.
something that can lead to more precise calculations.
Yeah. Dylan, does that explain?
No, but hopefully future lectures can
Yeah, I mean, your
alleviate my
question was
concern.
about the permutation. That this just happens that that's one thing that this is invariant to.
Okay. Actually, Prof, how long do I have like next week? Is there anyone presenting next week? I don't know whether we should
I think it's you and Liwei.
Each node corresponds to a separate data sample on its own, right?
No, the entire thing is a data sample.
No, so each node can be like a feature in your input space if you talk
Yeah.
about blur data.
So it's like if it's an image, it's like separate pixels of it. Is it?
Yes, each node will be a pixel.
Yeah, exactly.
In this case, the feature matrix for an image will be a 3-channel image, like RGB, values from 0 to 255 in the 3 channels. If it's a color image, if it's a grayscale, then the input feature will be just 1 dimension. Right?
Have people used GNNs successfully compared to CNNs for image processing? No.
So
right?
actually, transformer can be interpreted as a GNN. So people have used transformers for image vision transformers. Although I don't fully agree with the concept of vision.
No, there was one difference. It's a self-learn, if you will call it self-learn adjacency matrix
Right.
compared
So
to
in terms of transformers, the adjacency matrix is done through self-attention, which you can model using an attentional graph neural network.
Yeah, I think my biggest concern with a GNN is you need to actually separately formulate that specific adjacency matrix for a given problem.
So actually the beauty of transformers is that this adjacency matrix is self-learned through the data dynamically. So that's something that using attention, they did like soft weights for the adjacency matrix, which is pretty cool. Means that they actually define the graph structure based on what's needed. And I think attentional based graph neural networks are very powerful because of that. That's why transformers are so powerful, because they're like a graph neural network with some variable weight components for your adjacency matrix that is learned through self-attention. So actually you are jumping ahead already. This is actually going to be in the next few slides. But yeah, so we will see some relation between graph neural networks.
Should you promote sparsity then in adjacency? From what what earlier what Mihu said, if it because it's sparse, that's why it's advantageous, right?
So actually you may not want to promote sparsity if you are not sure what connects to what. But if you are very sure what connects to what, like in the CNN, then you can promote sparsity because like you are very sure that this particular node only interacts with like neighboring nodes. So you can promote sparsity because I've done some work on pruning also. So like making the weights 0 for like a neural network is actually learning something. You are learning that that particular connection is irrelevant. So if you have sparsity in your adjacency matrix that is like domain knowledge, you actually make the neural network learn faster, like what is done in the CNN. Because your filters is very narrow, it's only specific to that particular patch. Because we already know by domain knowledge that images, the pixels, only the neighboring pixels are important. So in some cases, having a sparse adjacency matrix helps with learning. Yeah, does that answer the question?
I guess it's like I understand. Okay, I kind of understand the balance between, as in you would like sparsity in general, because if you have less things to consider, it's like highly likely that, assuming of course the stuff you are looking at on your table are relevant to what you're seeking, there is less a trend you need to be concerned of, right? Because if there is sparse connection, less constrained essentially. But you don't want it to be too sparse that you're not connecting the full trend within that given data sample, you see. So how, if it, because it's self human constructed adjacency matrix, right, compared to, let's say, in transformer, how would you determine where to stop pruning the connection and where to just add more? What's the balance?
Well, since
Or just based on domain knowledge, is
we're
it?
talking about non-transformer methods, like
No, it's GNN now.
in a GNN depends on the type of GNN. So in GNNs that are not attentional based, the adjacency matrix are usually fixed. So it's like at input time, you already know what connects to what. Like social networks, you already know what is connected to what, maybe as part of the data structure that you get.
I think there is a subset of problem that you would like GNN to face, and it's not like a superior method to, let's say, I guess what you agree that. I think it's relevant more for tabular data other than other stuff. That's the only thing I can think of where a doctor can or clinician can come say, oh yeah, you shouldn't be connecting diabetes with how tall you are. So you should prune that because it shouldn't be how to say, it shouldn't be a factor in consideration in the first place. So you can actually construct well-formed adjacency matrix in this case. But other than tabular data, I don't think I can see why you would enforce, like, for example, GNN would be superior.
So it depends on the data type. So tabular data may not have relations. So you may not need such a powerful graph neural network that contains relationships between the nodes. You might just use an MLP. Or you can use...
Beg to differ. Actually, tabular data has lots of relations, especially for healthcare data. It's just that we do not know the relations. So it will be really helpful to have a method that allows us to learn that.
Yeah, but this adjacency matrix is a fixed thing, so cannot be
Yeah,
learned.
exactly.
So I
Yeah.
think using like attentional based methods are quite a powerful tool as well to learn the adjacency matrix. That can be done.
I guess attention is actually exploiting the fact that certain words are related based on correlations, based on how often they appear and how correlated they are. So they are exploiting that particular characteristic in text data, but we can't do the same for tabular data.
Actually, that's very true because the embedding space that people use for words already contain a lot of semantic meaning. They already cluster at the right spots, like men, women, already in the right place, king, queen. But for like tabular data, you may not get that kind of embedding because different features have different ways to be represented in. And one thing is that we haven't found a way to unify all the representations for the different features for tabular data. That's also probably why using tools like graph neural networks may not help that much, because if you cannot interpret the features the same way, it may not help to run it in the graph.
Yeah, I fully agree with you.
One thing I would say though, if you want to interpret this in terms of bias and variance, right, it conforms to the idea that if you're promoting sparsity for the adjacency matrix, right, the amount of functions you can represent from this graph, it's being shrunk. So it's higher in bias and lower, and no, yeah, it's higher in bias and lower in variance to a specific input data compared to, let's say, a fully connected structure. So there is that, assuming that the bias is correct.
Yes. Yeah. I think it's interesting discussion. Yeah, it just shows that how difficult it is to get tabular data to like correspond to the right representations. And yeah, that may not be a network structure issue. That may be a representational thing. But the representation actually is linked to the structure. The structure can actually help it learn the representation. Like for word embeddings, it is learned through an embedding layer, which is like basically a mapping layer into an n-dimensional like latent space. So if you can learn some form of representation for your tabular data, it may be possible to apply like techniques like graph neural networks. So let's say this is your input data for your tabular data, like input. So this is maybe your feature one. Let's call it feature one. And then we call it feature two. You can like sort of learn an embedding layer, maybe an MLP, where you have like you map it to an embedding layer. Something like word embedding. So you map it to an embedding layer.
No, Dylan, I think the biggest advantage of this is computation, right? Because you could have like millions of features. These graphs are going to get very big. And what the graph representation allows you to do is to use graph-based algorithms. Yeah.
So if you do
that's the
embedding
biggest
layers, you can potentially like help to solve some form of representation problem because you allow some form of like mapping to like a certain embedding to a certain like latent space. So actually, if you look at like the transformer architecture, before they pass it to the query key value branches, they actually have an MLP to actually do some form of mapping. It's a similar mapping that you see here, mapping to a representational space or latent space that allows it to compute this QKV in an efficient way. So I guess you could do that for tabular data as well. You could have an embedding layer, which is more or less like MLP. And yeah, that could potentially help it to learn the right representations if an MLP is enough to map the representation.